Hello guys, welcome to another episode of CUDA Education. We're just moving on in the process of working through ray tracing basic. Um, the last place that we left off as it relates to the linear timeline of this code was create the ray tracing pipeline, right? Um, I don't think it's a video directly before this one. It's a video another step before. So not the one previous, but the one previous to the previous. Okay, you guys are programmers. You could figure out which video that is, right? Um, so now I'm gonna skip over the uniform buffer stuff and the handle resize stuff. I think based on all the content that I have online and what we have discussed with swap chains and stuff, both the whiteboard and also just discussions in the code, you guys could kind of figure out, you know, resizing the window and all that stuff. So I don't want to spend time with this. We could gloss over this for the time being. Maybe I'll revisit it at a later date, because we do have to kind of manage the storage image piece of it, which is something that is particular to the ray tracing examples, right? But it's I've discussed the storage image in previous videos and stuff, right? So then we get to the command buffer, right? And this is basically, the commands that we execute, um, on the swap chain images and on the scene and all that. Basically that's what, Vulkan command buffers, okay? But we're addressing it in the ray tracing context, okay? Um, this is my first video on the topic, and I still need some time to fully digest all that's going on. So this video is basically just gonna be the first render pass, if you will, or the first investigation of this section of the code. Don't have too many details. I still have to investigate some stuff, but I think it would be good to at least start discussing some things, and maybe you could go off on a tangent and investigate some stuff on your own too. All right, so the first thing it does is it checks if the window has been resized, and if it's been resized, it triggers the handle resize function, which is directly above it right here. Okay, so that's pretty straightforward. Now we get, command buffer begin info. Um, so, this is like setting up and beginning the command buffer, stage, right? Now, VK image, this guy. Yeah, not sure what this is. It's a sub image resource, something of that nature. I'm not going to spend too much time on it right now. But the big elephant in the room for this command buffer, and for pretty much all of the examples that we have in this solution. So all of these examples here, this is the base class, um, is it has this draw command buffer as variable. It's like a vector, right? And it's a variable that we loop over for basically every example in the solution, right? And I kind of have been delaying, but I do need to do a video on this variable because it's very important. And it sort of is, it's crucial to the whole command buffer conversation, right? So I promise to dive deeper into this variable. I have to do some investigations myself. But pretty much what happens is that in all of the examples, we loop over this draw command buffers variable, and for each index, for each indices of it, of the vector, right? Because it's a vector, or like, you know, an array. Sorry, not a vector, an array. It is an array. So like for each instance, we put in instructions and we loop, right? So we're putting in instructions in each one and we're looping, right? Um, uh, yeah, I don't want to get into it too much right now. I was doing a little research on it before, but let's not yeah, let me not go on a tangent. Okay, so we, for each of the loops, we begin command buffer. Okay, so you know, we basically start, right, lower vk function, so we know it's important. And then we do this memory operation, set up the buffer regions pointing to the shaders in our shader binding table. Okay, so we kind of went over shader binding tables already. We kind of went over some memory stuff. Set up buffer regions pointing to the shaders in our shader binding table. We know that a shader binding table is an internal thing in the GPU that like the GPU itself manages. It's not like a table that it's not an Excel spreadsheet or something that we get to tinker with directly, right? But anyway, what I want to at least communicate right now is that a memory operation happens here, right? And you notice how, you know, we have a stride and a size and all that, right? So it's a memory operation. Set up the buffer regions pointing to the shaders in our shader binding table. Okay, so so that's this part right here, which, you know, we went over previously in the previous videos, right? um and I'm gonna leave that at that for now. But pretty much a huge memory operation happens where we, you know, we're connecting, I guess, the command buffers to we're connecting the command buffer to the shader binding table, right? All I know right now is that it's a memory operation. Um, and then the big goal of all of this is this guy right here, this lowercase vkCmdTraceRaysKHR, right? This is kind of, you know, at the heart of what we're doing, because now we're actually dispatching rays and um you know, we're doing the thing. So we reference, you know, notice that we have this vk strided device address region khr, and we're associating it with, you know, for each one of them, for the regen, the miss, and the hit, we're associating with the shader binding table through get buffer device address, right? Regen shader binding table, miss shader binding table, hit shader binding table, right? And it's all hitting these variables here, right? So we have a device address, a stride, and a size, right? So these variables now are put into the vkCmd trace raise KHR, right? Along with our command buffer. Not sure what the callable shader SBT entry is right now. And then we have a width and a height. Now, if you play around with this width and height, I will say that I'm not going to do it right now, but I will say that if you mess around with the value of this variable, you will get, because you could go to declaration, right? If you mess with this value, basically what I did is I just I changed this to like 200, but I didn't do it because this is in the base class thing and it's a header and all that, and it's like somewhere else. So I just created I created another variable up here using the using this. I did with CUDA. So I just created with CUDA up here equals like 200, and then I dropped that variable into here. And then what basically happened is that the entire triangle was basically compressed into a section. So um, you know, haven't fully figured out exactly what's happening, but this function right here controls sort of the generation of the rays, and sort of it does the ray tracing. Okay. Let me see what the official word of it is, just so I could say I said it. Right. Initialize a ray tracing dispatch. Right. So this is kind of at the heart of the code. We do a whole lot of work to get to this point, and notice that we're pretty much we're towards the end of the code. We're at line 765, right? But initialize a ray trace dispatch, right? And you need all this information to be put in it. You can't skip over the parameters or anything. I tried, believe me, I tried. But yeah, if you mess with this width, basically it compresses the region in which I mean, you will get the whole triangle. Even if you make the width smaller, you will get the whole triangle. But the triangle, like if I do a very, like the 200 I did, but the triangle is squished in the window. It's almost like it's almost like a line the way how the width is squished. So I guess I will get to that in another video. But this is initializing the ray tracing dispatch. And then after that, it's pretty much now we have to just do the logistics of managing the storage image and the swap chain image. So in the previous videos, we talked about the storage image and how the storage image is sort of an intermediary between the swap chain image and all the ray tracing and stuff, and we use the storage image to get more flexibility. So what happens here is that we have to just manage the logistics. So copy ray tracing output to the swap chain image. Remember, the swap chain image is basically one of the previous steps to us seeing stuff on our screen. So storage image, ray trace is saved into the storage image, then it goes over to the swap chain image, then the swap chain image we take out the blank image out of the swap chain, we write to it, or we copy the storage image, we put it back into the swap chain queue, right? And then we eventually present it to the screen, which then eventually makes it to your eyes, so you could see exactly what happened. So that is pretty much what this swap chain image, what all of this is doing. Prepare current swap chain image as transfer destination, right? So we're going from storage image to swap chain image. So you have to do an operation to do that. Prepare ray tracing output image as transfer source, right? So the transfer source, as you can see, storage image going as the source, swap chain image as the destination, right? I mean, there's a whole bunch of parameters that Vulkan uses to make sure, and then you have to do the actual copy, right? CMD copy image, vkCmd copy image, and then transition swap chain image back for presentation. So, as I said, we take the swap chain image, we copy it over, we modify, we copy stuff to it from the storage image, we modify it, and then we transition swap chain image back for presentation. So remember the swap chain is like a series is a queue of frames that are waiting to be presented to the screen. So believe me, I have like 3 or 4 videos on this, two or 3 videos. I mean, and I've discussed it in many of my videos, right? So, but check out the check out the whiteboard edition. There's a whiteboard presentation I did where I'm drawing. So we transition a swap chain image back for presentation. So and then that's what we see when we go to the screen. Transition ray tracing output image back to general layout. So it's this is basically it's basically resetting the canvas, right? So we've already copied what's, it's almost like you draw on a canvas, you copy that canvas over to the swap chain, and then now you need to clear the canvas to write something new onto it, right? Or to draw something new. So that's what transition ray tracing output image back to general layout, right? So that's what all this is basically, right? And then vkn command buffer, right? So that's pretty much the command buffer, right? So we're at line 800 now. The full code is about 910, right? So we're at line 820 now. Okay, so we're kind of making some progress, right? We're almost there. But yeah, that's pretty much all I wanted to discuss for this video, because like I don't really want to get in too deep, but at least let us prepare our minds for what is to come. So again, the command buffer, basically it's what we do to execute everything, right? And Vulkan works in terms of command buffers, right? So you have to speak the command buffer language. And then we have this draw CMD buffers variable where for each image, for each frame, for each image frame, whatever, we have a specific set of instructions for them, right? And we're looping over each frame and each, so that's what this is. Right, you see it says here, create one command buffer for each swap chain image. So CMD resize, so we're basically resizing the CMD, draw CMD buffers to match the swap chain image count, right? And this is in Vulkan example basic, which is part of the base class that is used for all of the examples pretty much in the solution, okay? So I don't really want to get into it too much, but this is what this draw command buffers, right? So we begin our command buffer, we do some memory operations to basically attach the shader binding table to the command buffer, so like everyone knows about each other and all of that, right? This is like a memory operation. Dispatch the ray tracing commands. So we bind the pipeline, we bind the descriptor sets, and then we do the vkCmdTraceRaysKHR, which is initialize a ray tracing dispatch. And then we do that. We have a width, a height, and some other stuff. And then now once we do the dispatch for this particular, because we're still in the for loop. So the for loop is from here all the way down to the end, right? So it's for this particular for this particular image, for this particular frame, all of that stuff. And then we have to copy from the storage image to the swap chain image, and then we have to reset the storage image after we've done the copy, right? Right, and we have to return the swap chain image to the swap chain queue for it to be presented, and right, and then reset the storage image, and then we're good to go. All right, so that's it for this video. I guess I will dive into it deeper in another video, but that is the command buffer for ray tracing purposes. It is it is it's significantly different. The memory operation is one thing. I don't think for the other examples we had this like specific kind of memory operation with the shader binding table and stuff. So the memory operation is different. Obviously the ray trace the ray tracing dispatch is obviously different. And then also, you know, we have the intermediary storage image, so we have to copy from storage image to swap chain image, and still manage the swap chain image and all of that. So that's different, right? So that's pretty much it. So this is the ray tracing basic example, this guy here. And a very long time ago, we did just the regular triangle, which, you know, obviously is not ray tracing. So hope you guys enjoyed this video. If you wanna be able to do all this and have this on your machine, if you have a Windows-based machine with a Vulkan-capable GPU, you need tutorial number 1 and tutorial number 13. Tutorial number 1 installs the walks you through installing the Vulkan SDK. Tutorial number 13 walks you through installing these examples here, right? It goes through all of the things and the how to set up Visual Studio, how to deal with the solution itself, CMake, all that stuff. So I pretty much walk you through the whole process, just like what I'm doing now. And you basically are able to, you know, to at least get it running on your machine. Make sure you have a ray tracing capable GPU. If you don't have a ray tracing capable GPU, you just have a Vulkan capable GPU, you would still be able to run all the other examples. It's just that for the ray tracing one, you wouldn't be able to run it, right? So that's all that. That's all that means, right? So this guy right here. Okay, this is the ray tracing, right? Yeah, guys. Thanks for rocking with me. That's all I have for today. I will continue to dive deeper into this and other topics. Do I have... Yes. All right. Bye.